Hi guys, we are discussing in the Z transform, and up to the last lecture I discussed what is the Z transform. As I told you, actually transformation means we have to transform the some value of function into the another form. Earlier I have studied Fourier transform, in which we use as a integration as a tool, and here we use infinite series as a tool. And I told you what is the Z transform, and then what are the properties of the transform, and also up to the last lecture I took some numerical examples to how you can use the transform to solve the numerical problems. Right now, today actually I told you if we have any sequence here, we take the sequence and we take the Z transform. So we denote this Z transform is a function of Z. Here this is capital Z that denotes the Z transform, and this is the small z that denotes the complex number z equal to x plus iy. Because I defined it as a series n equal to 0 to infinity and un sequence and z to power minus n. If we expand this, then we get infinite series in form of z, and so finally if we take the sum of the series by the help of Convolution Theorem or GP, then we will get finally a function of z. So we denote this u of z. Then what is the actually inverse Z transform here? Today I discussed inverse Z transform, and then what is the application of Z transform actually. Then if uz is the Z transform of un, then this un, which is a sequence, is actually inverse Z transform of u of z, right? So there are no some specific formula for Z transform. Basically, we have already find the values of the transform of given sequences. Now, so we can take their conversion, their inversion, and we can obtain various formula of the Z transform. As you know that if we take some standard formula, you know that Z transform of 1, I defined it as Z upon Z minus 1. This was the formula, and so by this formula, we can obtain inverse Z transform of small z upon z minus 1 is equal to 1. Similarly, we define second formula Z transform of sequence a to power n. We define that as z upon z minus a. This is a standard formula, and we can take simply this is inverse Z transform of z upon z minus a equal to a to power n. This is the second formula by the sequences and number of the formula which we have told. So we can directly obtain the inverse Z transform by the using of already calculated values of Z transform of the given sequences, just reciprocal form, no other formula, and by which we can find the inverse Z transform. So first here I will take up some numerical example of inverse transform, how you can calculate the inverse Z transform, and then main topic is there today I will discuss, that is the application of Z transform, because there are some types of difference equations and those can be solved and calculated by the using of Z transform. So first I am taking a numerical sum to find inverse transform, and then this one. That is, if we take example, find inverse Z transform of function 2z square plus 3z upon z plus 2 upon z minus 4. So this is the problem. Then you have to find the Z transform of this. If we take this, we have to find Z inverse Z transform of 2z square plus 3z upon z plus 2 and z minus 4. That is inverse transform. If we use here, that is you use here, then and you take this as, actually we take uz to have this is has to find. You use the concept of the partial fraction as you have studied at class 11 and 12 level, and by which you can solve this very easily. And here it is actually my solution here. Actually, uz is given here 2z square plus 3z upon z plus 2 upon z minus 4. You can write it as u of z if you take z is common in numerator and transfer on the left hand side. Finally, we get 2z plus 3 upon z plus 2 and z minus 4. Right? And by partial fraction, you write this as 1 upon sec z plus 2 minus 11 plus 11 by 6, 1 upon z minus 4. By partial fraction, this is, you know that this is by partial fraction. By partial fraction, you can separate it as, right, and now transfer z on right hand side, then it becomes z upon 6 z plus 2 plus 11 by 6 z upon z minus 4. Right? This is the using the concept of partial fraction, and you can separate two different terms of this quadratic expression. Now, so you can find the z inverse transform by directly formula. By linearity, we can write it as, now z inverse of 2z square plus 3z z plus 2 and z minus 4. That can be that is z inverse value of this. You have calculated z upon 6 z plus 2 and plus 11 by 6 z upon z minus 4 by the partial fraction. And now by linearity, you can separate it as, that is 1 by 6 inverse z transform of z upon z plus 2, that is 11 by 6, take it outside the expression due to constant value, and inverse z transform of z upon z minus 4. Right? And this is directly based on the formula. Just I told you, inverse Laplace transform of z minus a is sequence e to power n. Compare this. The first one is 1 by 6 plus 2, so minus 2, so minus 2 to power, and this is sequence plus 11 by 6, this is 4, so this is 4 to power n sequence. Right? And that is your answer. This is the expression, this is the required inverse Z transform. This is the value of Z, and here you will get inverse Z transform is a sequence of 2 times minus 1, 2 to power n and 4 to power n by this formula directly. The first concept is that if there is a fractional type of the function of Z, then firstly you have to take the application of partial fraction, you separate them into fractions of linear factor, and then use directly this formula, and you can find your required inverse Z transform. Right? And second thing, there is also a formula for the multiplication of higher degree of the factors, and that is a formula that is known as Convolution Theorem, which can be also used by such type of the functions. That is Convolution Theorem. Use a formula which is known as Convolution Theorem. First we take its statement. What is the statement? If inverse Z transform of u of z is sequence un and inverse Z transform of another function vz is take vn, then Convolution theorem states that inverse Z transform of uz into vz, simply that is this is equal to un into vn, or you can write it as also sigma m equal to 0 to infinity um and v n minus right, and m equal to 0 to n. Right. This can be also written as in this form, This is a statement of convolution theorem by which you can take, if we have a multiplication, huge multiplication, whose inverse Z transform cannot be calculated directly by using a partial fraction. So we can separate two parts and we can calculate inverse transformation separately, and then multiplying them we can obtain the required this. Proof is very simple, verification is very simple of this theorem if you take the verification or proof, because we have this one, inverse Z transform of uz is equal to un, right, and inverse Z transform of vz in another sequence vn, right, and by which you can know that is the Z transform of un equal to u of z, and Z transform of vn equal to v of z, and meaning that it can be expanded in form of infinite series as well as this. Now we have to prove this one. If we take this inverse Z transform of uz into vz, what is this, right? If we expand this in series, so we can open this by this is because this is that is inverse transform of un vn. Take this inverse transform, if you calculate from here, so this will be a series in inverse form, because vn is this is a series. If you open here vz, and this is also infinite series, and that is equal to the combination of this series. So if we take uz and vz first we take uz and vz from here. uz is, that is sigma n equal to 0 to infinity, that is un z to power minus n, this series, right, and another series is sigma vn z to power minus n, this one, right? Means this series is, if you open this, u0 u1 z minus 1 u2 z minus 2 plus 1, and this is v0 v1 z minus 1 v2 z minus 2 and so on. If you multiplying these series, finally what will you get? That is uz into vz. If we multiply this and take the nth term, if sigma, then this is u0. If you multiply nth term, here nth term is u0 is vn z to power minus n. If you take this one plus u1 v2 log n minus 1 and so on. Take this series. Finally you get un and v0, and where n varies from here, n varies from 0 to infinity. After multiplication we get this one, right, and this is multiplied by z to power minus n term, right, and what is this? This is actually z transform of u-net, v-net, u1 vn minus 1 plus 1 un v0, z transform of this. And so inverse z transform, if you take this one, so inverse z transform of uz and vz is equal to u0 vn u1 vn minus 1 plus 1 un v0. That is sequence, right? And that can be written as, if you expand this, so that can be written as un into vn, and that is your required right hand side. So this is the statement of convolution theorem. Means basic concept and main gist of the convolution theorem is that if you have an expression and you have to find the inverse z transform of that expression, and you cannot express into two partial fractions or fractional function and easily. So take one by one and individually you calculate the inverse Z transform and then combine them. And now more emphasize on this, and also what is the basic concept of convolution theorem and how you can use convolution theorem to solve such type of problem. Here I am taking a numerical example based on the convolution theorem. Then it will be more clear. That is example, find, use convolution theorem, evaluate inverse Z transform of 1 upon Z square. Z square upon Z square plus A square, Z square plus B square, and so on. Z minus A square. That is Z minus A and Z minus B. Take this one. You have to find inverse Z transform of this. So by convolution theorem, it can be very solved easily instead of using partial fraction. You can write it as inverse Z transform of Z minus A, take one function, into Z upon Z minus 1 function. Take this one, use it, take this one, vz it. Right? Then by convolution theorem, if we use convolution theorem, then this will be equal to sequence un into vn. Take this as equation 1. Now, separately we know that inverse Z transform of Z upon Z minus A, which is you are denoting un, is equal to sequence A to power n. Right? And inverse Z transform of Z upon Z minus B, which is to denote V of Z by formula, it will be equal to sequence B to power n. Now, simply substitute the values of this in equation number 1. We have Z inverse transform of Z square upon Z minus A, Z minus B is equal to A to power n sequence into B to power n sequence, right? By formula, you can write it as sigma n equal to 0 to n, A n B to power n minus m. You can write it as. If you further calculate this, then you can also find the sum of this series. If you open this, m equal to 1, this can be written as m equal to 0 to infinity. You can take b to power n outside and it becomes a upon b to power n. If you expand this series by putting values of m equal to 0, 1, 2, 3 and so on, we get 1 plus a upon b plus a upon b square and plus 1, last term up to n, last term a upon b to power n. So here n plus 1 term, and you know that this is standard GP with common ratio a upon b. So its sum is first term 1, a upon b to power n plus 1, right? N plus 1, n plus 1 upon r minus 1, common ratio is r. So a minus b minus 1. By formula, this is the sum of GP. If you calculate this, so here b to power n, if you take the LCM, a to power n plus 1, b to power n plus 1 upon b to power n plus 1 in numerator. In denominator, if you take the LCM, this 1 power is cancelled out, b to power n is also cancelled out. Finally, we get a to power n plus 1, b to power n plus 1 minus a upon a minus b. This is the answer of inverse Z transform of this expression by the using of convolution theorem. This is the main concept of the inverse Z transform. These are the main formula, main concepts by which you can find the inverse of Z transform. Now, that is the last topic of this chapter. That is the application of Z transform. Means how you can solve the difference equation. That is the application of Z transform. Actually, that is solution of difference equations. Here difference equations, and by using Z transform, actually you have to find the solutions of such difference equations by given difference equation with some boundary condition, in which basically you have to use shifting problems. You know that we have already in starting of Z transform, I have already told you shifting property, shifting theorem, in which I told you Z transform of sequence un plus 1, then it is small z of un minus u naught. This is the formula. The second formula I told you, u of n plus 2 is z square un u naught z u1 z minus 1 and so on. These are the shifting problems. Those can be used in difference equation. So to explain this, how you can use this, again I am taking here an example of difference equation, means using Z transform, solve the difference equation, for un minus un plus 2 equal to 0, given that boundary conditions u naught is 0 and u1 is 2. Right? This is the difference equation which you have to solve by using Z transform. Right? Un sequence un plus 2, boundary conditions, initial conditions u naught is equal to 0 and u1 equal to 2. How we can solve this? First, we take the Z transform of entire equation. Right hand side is 0, so it is 0. By linear property, it can be separated as, right? And if we denote Z transform of un is u of z, then first term is 4 times u of z. Second term, again by shifting theorem, shifting property, can be open as z square times un minus u naught minus u1 z to power minus 1, and right hand side is 0. Right? This is for uz minus z square. Un means you know that u of z and u0 is given condition, that is 0, and u1 is 2, or z power 1 means 2 upon z. If you open further, this is 4 times uz z square times u of z plus 2z. Finally we get this one. And here if you take common, uz is 4 minus z square u of z plus 2z equal to 0. If you find the values of u of z here, transferring the values on the right hand side, finally we get 2z upon z square minus 4. Right? This is the value of uz. So the second step, now we find this, and now what is uz? You denote uz is the z transform of un, so that is the un of 2z upon z square minus 4. Right? Then you have to calculate value of un. So un, you know that is the inverse transform of 2z z square minus 4. Now you have to calculate the inverse Z transform of this expression, and the value of inverse transform will be your required solution of the difference equation, and it can be calculated by partial fraction as you have done. 2z, factorize this, z minus 2 and z plus 2. If you factorize this by using partial fraction, so you will get z inverse of this one. You can calculate simply as you calculated inverse transform. This is very simple partial fraction. As if you take this one as uz and you have to calculate, if you take this one as uz or you calculate this, then it is very simple. That is uz upon z. This is equal to actually 2 upon z minus 2 and z plus 2. Now partial fraction is very easy. What is the partial fraction? This is 1 upon 2 times z minus 2 minus 2 times z plus 2. This is the simple partial fraction of this. This is plus minus. Right. If you calculate this is a very simple partial fraction. 1 upon 2z plus 2 minus 1 upon 2 times this one is plus and this is minus, because if we take this 2z or 2z is cancelled out, then 4 and minus 4 is cancelled out, and this 2 is outside this, and then 2 is also cancelled out. Finally we get z minus 2 minus z plus 2 and 1 by 2. This is the partial fraction. Finally, this is 1 by 2. This is 1 by 2. Because we get 4 and here we have to find 2. And now transfer this z in right hand side, we get simply value of uz is, that is 2 fractions, 1 upon 2, z upon z minus 2, z upon z plus 2. Right? And uz is defined as z transform of un. Now take the inverse, that is un equal to 1 by 2 by property, linear property, that is 1 by 2, inverse the transform of z upon z minus 2 minus inverse Laplace transform of z upon z plus 2. And I have told you the formula here. This is 1 by 2, that is the sequence 2n, and this is the sequence minus 2n. This is the formula, and if 2 is cancelled out, then this is un, and that is the basically solution of the difference equation by using z transform. Right? This is the application of z transform, and there are a number of sums in every book of difference equation. You can solve this. Means basically 3 steps are there. First, you take the z transform of given difference equation. Then you will get in left hand side and right hand side problems of the z transform. By the formula of z transform, solve them, and then finally you find the value of u of z. And if you get the value of uz, then simplify them and now take the inverse z transform lastly, and now solve the inverse z transform. Finally you will get the required sequences, and that is the required solution of given differential equation. Alright, okay, in this chapter difference equation you have to prepare these things, means z transform, inverse z transform, and then application of z transform. In application of z transform only you have to solve the given differential equation. Guys, and now from next lecture I will start your last unit, that is the Laplace transform. Okay, thank you.